Okay, am I still locked? Am I back?
No, you're back.
Okay, good. That's appropriate because we were just talking about how I need to check everything because I always have technical problems. And there we go. There's a technical problem, but I'm getting used to it now, so that's good. Alan, I couldn't hear what you were saying, but did you introduce yourself, or should I?
I didn't, because I didn't know where you were, so it's a little worried for your well-being there. Well, I'm Alan Hall. I'm the co-host of the Uptime Wind Energy Podcast with Rosemary here, and in my day job, I protect wind turbines and aircraft from lightning damage. So I've been doing this for quite a long time. Rosie, you and I have known one another for 15, 20 years or so, probably at this point. It feels like that at
feels
times.
like it. So Alan and I co-host his podcast together, the Uptime Wind Energy Podcast. And so I guess we met a year or two ago when you invited me as a guest on your show, and then later asked me to come back and continue. And we've continued to do that every single week pretty much ever since. So that's been good. So that's a good time to mention that you should sign up to the Uptime Wind Energy Tech News and also check out the podcast. The links are in the description. And also, Alan is from WeatherGuard Lightning Tech, and they're the sponsor of this podcast. So usually I say what they do, but Alan, you're probably better placed to tell everyone what does WeatherGuard do?
Well, WeatherGuard Lightning Tech makes lightning protections for wind turbine blades and for aircraft. So we make lightning protection for things that go fast. So all those blades that Rosemary designs, we try to protect them from lightning.
Yeah, even better than when they come straight out of the factory.
Definitely so.
Yeah, cool. Okay, so the latest video that was on Engineering with Rosie was about lightning and wind turbine blades. Pretty much the blades, not the whole turbine. So a lot of questions on that video, and Alan helped a lot with that video, and just has a vast amount of experience. So we're going to answer some of the common questions that were on the video, and Alan's already been in the comments I saw answering questions, but the format of today, we're going to answer, some of the most common questions. One of them most frequently asked was, how does the cable go through the hub without just twisting off? Because obviously, like if your wind turbine only spins one direction, it doesn't like go around and then go back around to unspool the lightning cable. So that's something I probably should have mentioned in the video. So we'll talk about that. We'll also talk about how wind turbine blades are like aeroplane wings or not like them, and how the lightning protection is the same or different, and a little bit about how blades have changed and the lightning protection philosophy, I guess, has changed as well since we have gone from, trying to avoid anything conductive in wind turbine blades, and now we have to accept that carbon fiber is here to stay, and how lightning protection has changed. Some things like that. And then what I want to do as well, I'll add a little fun thing in. I'm going to call it a lightning round because it's a nice fun. We'll have a lightning round, which will be like a Shark Tank like thing, where I'm going to take some of the best and craziest alternative lightning protection system designs that we've gotten in the comments, and I'd like viewers to tell us, number one, tell us where you're calling in, not viewing from today, because that always helps me. And then if you've got an idea for what's a better way that you could design a lightning protection system, or even better, a totally crazy way that you could design a lightning protection system for a wind turbine, then we'll go through and shoot them down, or get some ideas and quickly patent them.
Well, we could do that, Rosemary, but hopefully we're going to see some good ideas. I did go look through the YouTube comments when the video came out, and the comments were really good. Obviously, the Engineering with Rosie crowd is pretty bright and in tune with what's happening in the wind energy world and in the lightning world, evidently, because they had some really good ideas and were spot on in some cases of where the industry is headed.
Yeah, well, if you can remember any comments you specifically want to talk about, then we can I can bring them up. But otherwise, I'll just pick out the ones that I thought were good.
Okay.
But anyway, the first one, actually, someone already commented it before the stream even started. Someone commented on the exact question that I wanted to start with. So from MCK Sys AR, I'll leave my question now. How is the wire/mesh from the rotating blades connected to the turbine body? Are they using carbon brushes and copper rings, or is there something newer/better? So, and that one was asked, many times. So, Alan, do you want to explain how does the turbine not just twist off the lightning cable and break it?
Yeah, it's a good question, right? So each blade has a down conductor, basically a copper or aluminum cable inside of it, and that runs all the way from essentially the tip to the hub area. So at the base of the blade, it usually grounds out to the fitting. So each blade actually bolts. As Rosemary, well, maybe Rosemary, you can describe this, but each blade just bolts into the hub, correct?
Yep. Pretty much. It's the only way I've seen it done. Anyway. Yep.
So there's a lot of metal pieces in that in that fitting, right? So the hub's sort of a cast piece, and then there's all metal in there. So you're really only going from the down conductor to the base of the blade, which is metal, and having a jump there. And then, as Rosemary has described on her YouTube channel many times, the blades pitch, right? So there's a pitch actuator in each of the blades, so they do pivot. They put some sort of either a spark gap there to jump that gap, or some of the better designs I've seen lately are there's sort of a brush connection there. And remember, Rosemary has been very pointed on our podcast about wind energy companies trying to reduce the cost of wind turbines. And so some of these designs are really simple with basic materials. They're usually not using copper, because copper is expensive, and they're usually not using graphite because graphite brushes tend to be expensive. So they'll do things like this. And Rosemary's showing a good example here, which is a spark gap at the base of the blade and that sort of pivot ring where it's jumping the gap and making its way through the hub and down to Earth, eventually to Earth. These sparking events inside the blade, at the base of the blade, are pretty common for some of the designs. There's one manufacturer in particular that likes to do that. From Rosemary's perspective, and probably my perspective, I think this is incredibly dangerous. There are 50,000, 100,000 volts across those two metal pieces there, and it's something that you shouldn't be touching or YouTubing, more importantly.
Yeah, right. Well, I hope that nobody is anywhere near the wind turbines when there's lightning in the area. I know that when I've climbed towers, that is definitely something that they're checking for to make sure, if there's lightning forecast, then you're not climbing up any turbines that day. So yeah, but this wasn't an aspect that I paid a lot of attention to, I'll be honest, because I was working with the blades when I was working for a wind turbine manufacturer. I definitely worked with the lightning protection system in the blades a lot. But my understanding is that every manufacturer does this in a slightly different way. Is that right, Alan? Yeah.
True. Absolutely true. Yeah. Every OEM tries to reduce the cost as much as they can to simplify the lightning protection system. It's an added expense in some level, so they try to make it as easy and simple as they can. One to lower cost, but two to also make it more maintainable in the field. So, as Rosemary can attest to, they're relatively simple systems today.
Yeah. Okay. We've got a question about this sparking design from Mike Klein. Aren't sparking events corrosive?
Yes, definitely so. Yeah. So anytime there's a sparking event, there's ozone and other radicals that are created because you've heated the air up, and you're pitting the metal material. And I've had a couple of more recent questions at the wind turbine conventions, one in New Orleans most recently, where designers of bearings and coatings for metal parts, gears, that kind of thing, where they have special coatings on it to make them hardened, have seen static discharge damage happen inside the gearboxes. And this is how it happens. There's a pathway through the gearbox, and arcing and sparking will damage those coatings and eventually damage the gears and the bearings and the raceways inside the turbine. It's not good.
So what's the plan, that it just doesn't happen often enough for that to have a major effect?
Oh, I think it has a major effect because the people I've talked to that fix those systems say it's something they see in the repair world. Now, there are ways to mitigate it, and I think it's just where if the OEMs are really looking at it, you don't have a lot of time. Notice maybe you can describe the amount of time you have with a new wind turbine blade and new wind turbine design is what, a year or so, and and it's out in the field. How long before it goes into production?
Well, it depends if it's a major change or a minor change. Actually, like just a standard kind of, slightly different size of wind turbine than the previous one. The blade part of it might only take 6 months. That's kind of a standard development time for a new blade. But the turbine itself, like maybe a year or two, or maybe several if it's, different in a lot of ways to previous turbines. And then, you might get 1, maybe 2 years if you're really lucky of your test turbine operating in the field before you are like, yep, okay, this is our design and we're going into serial production. So it's not so long when it comes to something like lightnings. You get struck, hopefully you get struck a few times in that period, but you don't know how strong the lightning was. And it's all statistical because, like it might be that lightning does what you expect 9 times out of 10 or 99 times out of 100 or even 999 times out of 1,000 would still be enough of a failure rate that would be a big problem once you've got tens of thousands of turbines out there. So
exactly. Right. So the amount of time you have as a designer to watch some of those effects happen is relatively short versus the 15 to 20-year life cycle of a wind turbine in service. So a lot of the designers don't get to see a lot of that damage. The repair technicians see most of it, and the companies that repair wind turbines see the long-term effects of those static discharges.
Yeah. Okay. We've got a couple of questions that are related to this sparking design. I don't know so much about it, so I'm just going to put them up. And so we've got coated bearings are used in Tesla motors to avoid that. And then Conservator asks, are the conductive lubricants for the gearbox? And got no idea about the pros or cons of that and whether it's implemented.
Yeah, so conductive lubricants have been used in really particular applications, really unique applications, mostly to do with rotating fittings, and I've seen it used in aerospace applications, some military applications. So in a wind turbine, it would just be so expensive they wouldn't tend to do it.
Yeah, okay. And I think that's a really key point to add. Maybe we'll move on to the next question that I wanted to do, which was how wind turbine blades similar or dissimilar to aeroplane wings, and what what's the consequence for lightning protection system? Because from my perspective, when I was working in for a wind turbine manufacturer, I was working on the de-icing systems, and that's another thing that is similar between wind turbines and airplanes. When an airplane flies through a cold cloud, then it's going to get ice building up on the wing, and that's bad for the aerodynamics. And exactly the same when a wind turbine blade spins through a cold cloud, then it builds up ice and it's bad for the aerodynamics. But the big difference that people didn't realize was there's a few differences, but for me the key one, for any time that someone wants to take an aero industry technology and apply it to the wind industry, is cost and maintenance. Wind turbine blades are cheap and infrequently maintained compared to aeroplanes. Do you think that's is that a good summary of the difference? And
it is, and airplane wings just serve a different function, right? They're both, wind turbine blades and wings are doing similar things in terms of aerodynamics, but that's where the similarities essentially end. Right, a wind turbine blade is not carrying humans, and obviously an airplane wing is. Airplane wing is full of fuel that's explosive. A wind turbine generally is not, contrary to some Twitter videos you may have seen. So there's just a whole different design effort going into a composite aircraft wing. And I worked for a number of years with a composite wing designer in Belfast, Ireland. And the amount of effort that goes into the design of a composite aircraft wing is astonishing versus the quick turnaround time that Rosemary was put under when designing composite wind turbine plates. It's night and day. It's just a completely different thing. Now, lightning protection wise, because aircraft wings carry fuel, you really add a lot of lightning protection. And if you think about just the way a wing is designed, it's just a box full of fuel. There's no barrier between the outer skin of the wing and the fuel. It's right there. So you have to do things like prevent sparking in the fuel tank, and that sparking is the European and the FAA regulations have a requirement that the sparking cannot be greater than 200 microjoules. 200 microjoules spark is something you can barely see. And so in order to prevent that kind of sparking happening in a wing fuel tank, you end up putting a lot of meshes, and mostly copper meshes, sometimes aluminum meshes, on the aircraft wings to protect the inside of the wing. On a wind turbine blade, we do use mesh, as Rosemary can attest to, but it's not as prevalent. And it's only used in particular locations, particularly if the blade has some carbon added to it, like a carbon spar cap or something of the sort, where they add mesh generally. It's expensive. It's sort of a pain in the it's an engineering pain. Manufacturing wise, mesh is terrible. Yeah.
I was working on a conductive blade heating system one time where we tried to use mesh to protect it, and that's one of the methods that a lot of manufacturers use to protect you put a carbon fiber heating element across the surface of a blade is one of the ways to heat them. And then it's not, the carbon fiber is conductive, but it's not thick enough that you can put a lightning strike through it and have it just survive that. So you have to discourage the lightning from going into the heating element or into the structural carbon fiber. But mesh, wind turbine blade, it's curved into two different ways, doubly curved, they call that in composites. So you can imagine like a piece of fiberglass or a piece of carbon fiber drapes nicely. It's just a piece of fabric, and it's that it will stretch and distort a little bit to accommodate the curve. But a piece of copper mesh is not very drapable. So that's your first challenge, is getting the pieces so that they they fit the profile properly. Biggest headache though is that you get little bits of it fall off. It's it's sharp, it's sticking into things it shouldn't, it's making short circuits, which really sucks for the heating systems in particular. You can cause some damage that way, and obviously destroy the functionality of your system. So so hard to deal with copper mesh. I think that's probably everyone's least desired solution, but it does get used.
And the difference between an airplane and a blade is a blade's got to remain in service in remote locations for 20 years, and an airplane lands after every flight, hopefully. So there's somebody looking at the airplane after every flight. And so we as airplane designers can reduce that mesh thickness, make it a lot more drapable. Because we know if the airplane gets struck, it may be grounded for a while until they can repair that mesh and get it back to original state. When a wind turbine blade, that may spin for a year or two before someone can attend to it. That's what happens. And so you end up in the wind turbine side using much thicker meshes that are just unworkable, in my opinion. I don't even know why we do that, but there's just a lot of effort to put lightning protection on these newer blades, and mesh is one of the things that's being incorporated now.
Yeah. Okay, so maybe we can talk a little bit about how blades used to be designed and how they are now, and especially we talked about that a fair bit in the main video. The main thing I want to add is, what's your perspective on what you're seeing in the field? Because obviously with your work you're going to talk to people who have a problem with their lightning protection system, right? So they've got wind turbines that have a lightning protection system installed by the manufacturer, and your product is something that they would add on top of that. And there must be a reason why they would bother to do that. So I thought you must have some good insights on what kinds of failures you're seeing and why. So I might just start, before I let you answer that. I'll keep talking a bit longer. Before I let you answer that, I'll just talk about my experience working with lightning protection, because I kind of feel like when I was at in that job at the manufacturer, really spanned the before and after times of lightning protection, where it's old school to new school. And the old school way was nothing conductive in the blade whatsoever past about maybe 10 or 20 meters into the blade. You can't put anything conductive, and that includes no metal staples holding bits of balsa wood together. No, if you've got a sensor, then it's going to be a fiber optic cable connecting it to the root of the blade, because you can't run an electrical wire through there. You can't put even a wireless sensor that has metal in it. Even so far as one of the main lightning guys at the company I was at forbade every factory from having any black marker pens, because some of them contain bits of carbon which are conductive. And he claimed that he saw in the test facility one time, he saw lightning attach onto a bit of black marker. So, people took it really seriously. Then carbon fiber came in, super conductive, but it's structural benefits and, in the end, economic benefits. You make the blade much lighter, which means that all the rest of the turbine components can be, smaller, lighter weight, cheaper. All of a sudden, we couldn't do that old strategy anymore of keeping anything conductive out of the blade. So we came up with multi-receptor designs because we didn't know where it was going to attach, mesh. What other changes did you see, and how did you see that perform in the field?
Well, the transition to longer blades and particularly loading them with carbon, and Rosemary, I think I saw some of your early designs when I worked at the Lightning Lab. The amount of carbon you would put in a wind turbine blade is dramatically minuscule versus a carbon fiber airplane wing, right? So in wind turbine, because carbon's expensive, right? Carbon fiber is expensive, and so the amount of carbon fiber that's going in there is not huge. So early on, the issue was if you had a lightning attachment to a minimal amount of carbon fiber, that the carbon fiber couldn't carry the energy. And carbon fiber is, as Rosemary knows, and I think, Rosemary, you saw some lightning testing around some of that. Carbon fiber is a decent enough conductor. It will carry some amount of lightning energy. It's just a question of how much. And as carbon fiber structures get thicker and thicker, they can carry more and more energy. Early on, because there's just a little bit of carbon fiber, it wouldn't carry the energy, and you'd have big amounts of damage in the lightning laboratory. And then everybody started to scramble after that, and a whole bunch. If you look at the design efforts, the patent efforts, starting around 2003 to 2010 ish, there was a lot, and then there's sort of a second wave just after that on designs. Everybody's scrambling. I think early on, and Rosemary, I don't know if we've ever talked about this, but early on, wind turbine blades, in order to be type certificated, right? So it's like an airplane in a sense. They get a type certificate.
Might be a better way to say that.
Well, I'm throwing the American version of it out, right? So for airplanes, we get a type certificate, which means the design has been approved and it meets all these requirements. And blades get something very similar, right? So one of the requirements was that they needed to have some lightning protection. And for early on, because blades are so short and were mostly made out of fiberglass, and that all they had to do was an analysis. So you had to put a certain number of lightning receptors, these little coin-shaped bits of metal on the outside, and run a cable down in it. And that was it. They wouldn't really test them at all. It didn't happen until they the blades started growing, and they started having issues out in the field, that they started doing some lightning testing. And then that became a standard around 2010. And then there's a more recent update to that a couple of years ago. But the damage you're seeing increases as the blades get longer. So as everything gets taller, you're getting closer to the sky. You're actually creating a new kind of lightning, upward lightning, that really changes the whole dynamic of what you're doing for lightning protection. So the industry had to learn from that, and they learned through the school of hard knocks. Their customers would complain, and the engineers would go out and look at these wind turbines that have been damaged by lightning and try to figure out, like, what the heck happened. And it became, and as Rosemary knows, you spend a lot of time in testing in the test world. What you see in the laboratory and what happens in real life can be two wholly different things, which is where the engineer comes in, right? I mean, engineers like Rosie and me and thousands of other engineers working at the manufacturers try to connect the two, right? Try to see what's happening in the field and try to recreate that in the laboratory or in a test environment, so we can understand what's happening and react to it and design better products. So blade punctures, pretty common 10 years ago, 15 years ago, really hasn't changed all that much. As blades have gotten taller, the problems have increased with that, and adding carbon, adds another level. Some of the more, I think Rosemary knows about some of these things, but some of the more recent things we've seen is with these carbon spars they're having. And Rosemary, you did talk about it in the video, in the YouTube video, flashovers inside of the blade, where the down conductor and the carbon spar are sparking between the two. Not good.
Yeah, try to avoid that. I think I've got to bring up the my editor made a little animation about that. I want to bring it up.
It was pretty good, actually. I think it's hard to envision what happens inside the wind turbine blade when it gets hit by lightning, but it's a light show inside the blade and outside the blade. There's a lot of electrical activity happening inside that blade. Remember, blades sit in the dirt and the muck and all the outside world, so they're not pristine, clean structures internally. So there are current paths inside of them. And
actually, I've got some. Sorry,
go ahead.
I just want to say what I'm showing here, and then keep going. I just got some pictures from Boeing about the lightning protection system of aeroplanes, and so you can see the puncture damage where lightning enters and exits. But yeah, keep going.
There's an exploded antenna. There's lightning strikes to the side of an airplane. Yeah, lightning actually, an airplane moves through lightning. In an airplane case, the lightning is stationary. The airplane's moving fast enough that it just kind of goes down the sides of the airplane and leaves these pit marks everywhere, which are a nuisance to mechanics because they have to go fix them all. And building carbon fiber airplanes like the 787 or the Airbus A380, the Airbus A350, the level of complexity there goes up. But they're beautiful airplanes. But internally, like this is a good example here, Rosemary, of what happens on an airplane. Airplanes, we've flown enough airplanes through lightning strikes that we have a pretty good idea what happens. And we actually recorded the pit marks on the airplanes and went, well, it seems like a lot of big energy strikes happen towards the nose and the tail and on the wingtips, and lower level strikes happen to the middle of the fuselage. And so we design the lightning protection systems to what we had seen in service. And at the time that we did that, we were making aluminum airplanes. So we had a lot of data on aluminum airplanes, which are lightning protection wise are really simple to design. And when we got to doing carbon fiber and all kinds of crazy materials, we had a really 30, 40, 50-year understanding what was happening so we could address it. And wind turbines are doing the opposite. You're doing the most complicated thing first, and then trying to figure out what's happening in the field. It's just a totally different way of going about it because of the nature of the business.
Yeah, and we're still catching up, right? The old system, it was kind of the same, where we had heaps of information about how lightning strikes attached to a fiberglass wind turbine blade with nothing conductive in it except for the receptor and the lightning cable. And now we're only a few years into the new designs and longer blades. And so we're learning.
Oh, you're learning a lot. And this is why things like drone inspections on wind turbines are so critical, and getting that data back to the lightning community is really important, because the engineers can't react to something they haven't seen. And when the manufacturers get data back from the field, hopefully in drone images, but sometimes through TikTok, they react, right? They try to understand what caused those situations, what kind of wind turbine blade was there, what was the situation, what was the kind of storm, was it in the wintertime, was it in the summertime, because those are completely different animals generally. What part of the world was it? Lightning strikes in Japan, particularly on the west coast Japan, are notoriously terrible, extremely strong. Some of the biggest lightning strikes recorded have happened on that western coast of Japan. And there's a number of wind turbines there. It's actually very windy there. And so we're putting wind turbines in some really difficult locations, and we're learning from that. And the Japanese researchers have done a tremendous job of watching and monitoring and video and photographing and instrumenting wind turbines and recording those lightning strikes to wind turbines. And that's how we learn, is that they publish papers based on that, and we figure out how to move forward.
Yeah. Big learning process.
Mm.
Let's do our lightning round now about the ideas about alternative lightning protection. So
All right, here we go.
anybody watching that still has an idea that haven't commented, then put it in there, and then after that we'll come back to how lightning systems are operating in the field recently.
Are we going to pick a winner, Rosemary? Are we going to pick a winner?
Yeah, we can pick a winner each, or maybe we both agree on the same one.
All right.
Okay, so this one, I should try and find I'll find a sensible one first, and then maybe we can cover some funny ones as well. Okay, so there's two from Mike Klein, who did mention that he had to leave, so he's not watching anymore.
Okay.
So he's got one, Faraday cages,
yes,
and two, rubber boots surrounding the base of the tower. So let's start with Faraday cages. And can you explain what is a Faraday cage, Alan?
It's just a metal cage, just like a bird cage, and you can protect everything on the inside of it from lightning strikes on the outside. So it provides shielding. That's what a Faraday cage does. Wind turbines, I'll relate a story to you, Rosemary. I don't know if I told you the story. Early on, wind turbines and then the cells were just made out of fiberglass. And so there's a lot of electronics, as you know, that run the wind turbines. And electrically, those fiberglass covers provided no shielding. And so the wires are just generally exposed. So when the wind turbines would get struck, it would induce a lot of energy inside the controls boxes and cabinets and everywhere, and it started blowing up equipment. And then designers realized that was a problem and started providing more protection to the wiring and making Faraday cages in the nacelles through different means that provide shielding. Yeah. So a Faraday cage is just basically a bird cage cover to protect the equipment inside.
Yeah. And I mean, so my understanding is that maybe it's used a bit informally, slightly incorrectly. It's not just like you would think copper mesh acts like a Faraday cage, but I was told it's not a Faraday cage unless it's like totally enclosed. And then it excludes the electrical field from anywhere inside. But maybe that was just someone being picky.
Yeah, I mean, right. It's the physicist versus the engineer kind of discussion, right?
Yeah. Okay.
Everything costs money, so you try to reduce the amount of metal you're adding to a wind turbine to keep the cost down, but you add just enough that the equipment works properly. That's the goal.
Yeah. Yeah. Okay. So what's your thoughts on Faraday cages? I mean, to a certain extent, the concept is included, so it's obviously not a dumb suggestion, because that's what a lot of people are.
Well, I think that actually is a winner, right? So the wind turbine manufacturers are using it for the nacelle. They're creating a Faraday cage. For the blades, you really can't do that, right? But it is an absolutely correct suggestion for sure.
Okay. Next, also from Mike, rubber boots surrounding the base of the tower. So I guess the idea is that there is no conductive path to Earth anymore. Would that work? First of all, would that work, and how well?
I'll use an analogy here, which I don't like to do because then I'm an engineer. But airplanes are not connected to the Earth either, and they still get struck by lightning, and they're miles above ground, right? So any kind of plastic rubber piece you put between the wind turbine tower and Earth is just going to be flashed over by the lightning. By the time the lightning actually hits a wind turbine, it's traveled usually a couple of miles. Jumping over a piece of rubber is easy at that point.
Okay, so this one is a loser. Sorry, Mike.
1 for 2, not bad.
Here's another one that I like in a kind of sensible side of things. If the blade is conductive, is it possible to electroplate copper conductors to the surface?
Yes, absolutely. And we do that on airplanes a little bit. We do electroplate parts of composites to make them conductive. The issue is usually when you electroplate, you don't have enough material there to carry the amount of energy that lightning will deliver. And so the first time it gets hit by lightning, it just vaporizes. So it works one time and it works extremely well, but then you have to fix it. And on a wind turbine blade, it just doesn't make a lot of sense. But it is something that we definitely do.
Okay. All right. So now I'm going to go to one that I get told a lot. A lot of people, you must get it even more than me, because, I'm only tangentially working with lightning, but people go out of their way to tell me their, amazing ideas that they have for protecting wind turbines. And this is one that it's probably the most common one that gets suggested. And Tim Dixon has just just commented it, fly an array of kites or balloons around the turbines, and presumably with a something conductive through there. So who was that? Wasn't there a US president who flew a kite with
Rosemary
Franklin?
Yeah, it was Ben Franklin, who was not a president, but
he
a really
wasn't a
smart
president.
guy. No.
Why not?
Well, he was smart enough not to be president.
Why did I get the impression he was a president? Did you?
Because he's on the money, right? He's on the currency here. Yeah. So, but Ben Franklin was a really smart guy. In fact, he was really the first scientist to recognize that lightning was some form of electricity. In fact, and he annotated positive and negative, what was positive, what was negative at the time. They're backwards, of course, because you just guessed at it.
He's the one we can all blame for having to deal with the concept of holes instead of electrons
exactly
flowing.
Yeah, that's all Franklin's fault. But that was in the 1750s, so we can take some of the burden off of him, because there wasn't much to go on at the time. But that concept of putting up tall towers, flying kites, flying balloons can be done, right? I think if you were trying to protect an individual wind turbine, you see this around rocket launch facilities like at Cape Canaveral. You'll see when SpaceX is launching their Falcon 9, there's a couple of really tall towers and some catenary wires, cables that are tying them together that provide a shield around that. Extremely effective. In today's world, where Rosemary wants to put out 200 wind turbines at a time at a site, and you're covering thousands of acres, it's pretty hard to do that and to maintain all that equipment. So the manufacturers have decided to put some protection in the blades. But it's not a horrible idea, right? I think early on, I would totally do that. If I had a wind turbine in my backyard and want to make sure that it lived through a lightning strike, yeah, you could do that.
I guess that you can keep an eye on the forecast and only fly it when you know that there's a storm. You don't have to stand there with a kite 24/7.
No, I hope not. No.
Yeah. Okay. So that one, not as silly as it maybe seems at first.
Not silly. Yeah, no. Real.
Then, another suggestion that I get semi-frequently from David Montgomery. Have you tried directing lightning to your blades with a rocket trailing a spool of wire for testing, or could also be used to direct lightning away from turbines? So maybe that's kind of related. And I have a little video to play that you shared with me, Alan, so you can explain what's going on in this video, if you remember.
This is rocket trigger lightning that was conducted down in University of Florida, Gainesville. And they have a lightning research facility down there, and they were one of about 3 different places, if I remember correctly, that would do rocket trigger lightning early on. So there was like a model rocket with a spool of thin copper wire with some, I think, a fiberglass strand with it too, to keep it together. So they would, in the presence of lightning, they would measure the electric fields that are around the launch facility. They get strong enough and they shoot this rocket off, and it would discharge the cloud. So it does work. It takes a lot of equipment to do it. As you can see here, there's a lot of instrumentation and a number of things to keep people safe, because you are discharging, you're having to control lightning discharge to Earth. Everything around it needs to be protected against that. So it does work. You could do it. The question is, if you had a rocket that failed and then the wind turbine got struck, you're kind of back where you started, right? That you have to be nearly 100% right on any kind of technology you would use. But conceptually, absolutely could work.
Yeah. Okay. I just want to point out that another viewer also suggested the rockets with wires. So I just want to delve into what's happening here a bit more. The rocket is triggering the lightning strike, right? It's not that you have to watch and fire a rocket at the exact time a strike is coming, and that will convince it to attach. What you wait for. No. It would still need to be a storm, right? You can't just do this on a blue sky day and create lightning. But if you've got the potential for strikes in the area, then you fire off a rocket, and then the lightning goes there instead of to something else. Is that it?
Right. Yeah, and the lightning strikes they're seeing here are very similar to a lot of lightning strikes caused by upper lightning. And upper lightning is an effect that we're seeing more and more of it as the wind turbines get taller, where instead of the discharge happening from the cloud and sort of traveling down to Earth and you see the big flash and explosion, The event actually starts from the wind turbine or building or whatever. It starts to reach up to the cloud, and it actually pokes the cloud hard enough that it discharges. And rocket trigger lightning is like that upward lightning strike. So they're similar in the way that they respond and the way that they move. The thing about this video, Rosemary, was you can actually see lightning being blown by the wind. So lightning is a physical thing, right? And once it's created, there's just a conductive bit of air, a filament of air, and it gets shoved around. It becomes a physical object. So it's plasma, right? So there's just this column of plasma, and you can push it around quite a bit. And it's hard to think about that way, but it is a physical, lightning is a physical thing. And in relationship to this, from rocket trigger lightning, some of the things that we learned was, and just monitoring lightning more closely, is when you watch a lightning flash in nature, you see that first big bright stroke, that first bang. The second pulse, so lightning will flash a couple of times, typically 3, 4, 5, 10 times. That first flash may land someplace you see it. The next part of that lightning strike may occur kilometers down the road. And lightning will move around like that. So once it attaches to something, it doesn't necessarily stay there for the whole event. It will bounce around in like 30, 40% of the cases, which you wouldn't assume that. But once you see it, it's like, oh yeah, it's a really unstable thing. Lightning is, the lightning channel is extremely unstable. And if one branch of it weakens or becomes less conductive, the cloud, all the energy up in the cloud will find another path to go, which is what it does.
Yeah, I think that's part of the challenge, that it is pretty unpredictable still from what we know about it. And so it is hard to design something where you know how it's going to behave when struck by lightning.
Well, there's a lot of physics to it, right? So lightning is a combination of electricity, right? And most mechanical engineers do not like electricity. They learned that early on in engineering school. And it's physics, it's thermodynamics, and it's aerodynamics, right? It's all of those together simultaneously. So we're just now being able to sort of relatively model how lightning moves in airflow. The French have done a tremendous amount of work with that through Airbus mostly, and Dassault in France to look at some of those things. So it's a very interesting space, and there's a lot more to learn there. We're just scratching the surface about lightning. We don't know a lot about it. Weirdly, we've watched it for thousands of years, right? But we really can't recreate parts of it in the laboratory. We just can't. There's things that we don't know what triggers it, what starts it. We don't understand some of the physics around it. We're instrumenting towers, we're watching lightning strikes all the time, trying to learn more about it. But when it comes to you and I trying to protect wind turbine blades, it's still a complicated problem because we just don't have all the answers. We're still learning a great deal.
Yeah. Okay. Back to this rocket video. Is it trailing a cable, or is it just? It is. Okay.
Yeah. There's a very fine copper wire behind it. Yes.
Okay. Cool. Let's just do a couple more, and then we can go back to the other last couple of topics because we're nearly running out of time. So I don't know if this is a serious suggestion. Maybe you do. Has anyone suggested the laser lightning protection yet from Central Down Climber? Is that's a thing?
Yes. Oh, yeah. Yeah. And we talked about it. I don't know if you were there for that podcast, Rosemary, but we did talk about it on the Uptime podcast over in Switzerland, right? There's been some more recent tests where they have trigger lightning with a laser. Now, it's super complicated. You need a pretty high power laser, and you have to have the timing right to do it, but they have been successful more recently doing it. The issue is when you fire that laser up in the sky, you have to cordon off the airspace because you can't have an airplane flying through when you light off this laser. So it does make it a little difficult, but conceptually it does work. And there's been a lot of research done in the last 20 years, I'd say, about it. Pretty successful. Yeah, it's an interesting technology.
And how much power does it need? Is it because obviously
I don't remember.
Because you need it at a time when the wind farm itself isn't going to be generating during the storm. It's probably shut down, or maybe it's not. I guess, but probably it's not generating. And I mean, they do have a connection to the electrical grid. Obviously, it goes both ways, and there's auxiliary power in the turbines that needs to be there even when the turbine's not generating. It's not like a turbine doesn't first take what it needs for its computers and lights and stuff and then send the rest. It's more of a, it's getting some and giving some at the same time, right?
Yes. Exactly.
Okay. So that one's pretty cool. I will admit that I am biased towards any solution that includes either a laser or a robot. Those are my two things. So if you could maybe get like a robot drone with a laser system attached to it, that would probably be my winner. But just one more suggestion before we make a judgment, and I don't know what this is. Maybe you do. If you don't, then we probably won't be able to judge it. David Montgomery says, Ben Franklin used a kite to attract lightning. Could you charge a giant Leyden jar or just direct lightning to ground? What's a Leyden jar? Am I
A capacitor. Right? It's basically a old style capacitor. Yeah.
Right. Okay. Yeah.
Yeah. Could I use a Leyden jar or direct lightning to ground? Yeah. I mean, all these ideas, which are completely valid, and you're trying to get the energy away from the wind turbine. I think that's a really good idea. And in fact, as Rosemary knows, a lot of wind turbine farms have Met towers. They may have multiple Met towers. And if properly placed where those Met towers are, you can use them to attract lightning and keep some of the lightning strikes away from your turbines. The lightning strikes that we're seeing more often now happen to be upward lightning. And upward lightning is sort of a triggered event. Here in the States, you see a lot of upward lightning. In fact, we were looking at the data. Everybody remembers back about a year ago, there was a wind turbine that was on fire, spinning around, and we all saw it on Facebook, wherever social media channels we watch. We've been looking into that more recently to figure out what kind of lightning strike that was, and it looks like it was an upward lightning strike. And upward lightning strikes start off with a positive lightning strike, and Tom Warner and a number of other researchers have documented this process. So in a regular thunderstorms, bang, 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 there's thunder everywhere and lightning. There it is. There you go. There's a positive lightning strike about 5 kilometers away. And then what looks to be upward lightning from this wind turbine and a Met tower just near this wind turbine reached out to the sky. This blade caught fire. There's a lot of turbines in this farm. If you look at the data, there's a lot of lightning strikes to a lot of turbines. So the vast majority of the turbines had no problems at all. This one had a problem. And
that's a understatement.
Yeah. So this one, I think we have worked with companies like Aeroplane in Latvia who do a lot of blade inspections. They measure the LPS systems, make sure the cables inside the blades are still connected like they should be. And they found like 15 to 25% of the cables are broken inside of the wind turbine blades. Now, who knows here, but if that cable was broken in this particular wind turbine, then there would have been a lot of arcing and sparking and heat inside of the blade, which could catch it on fire. Vaisala, which is the company that does the remote tracking of lightning strikes, they have a lightning location system. They have a number of sensors stationed all around the world. So when lightning strikes, they know where it is exactly, what time it happened. They know the amplitude. In this particular, I went back and looked at the data about this one. They said this lightning strike to this turbine had the capability of causing a lot of melting, which means there's a lot of energy in it. And as we see here, Rosemary, it looks like it just couldn't handle the amount of energy that was thrown at it. Yeah. Shocking.
Yeah. Literally shocking. Okay, we've really deviated from the point of a lightning round, which is supposed to be that it's fast, and we've just used up all the second half of the live stream. But that's
do we pick a winner? Can we pick a winner?
Now we need to pick a winner. But first, there's one more that just came up after I said the last one, which I have to include. Where is it? Here from Tom Dixon. Run the rotors backwards to blow the storm away. And that's
I like it.
That's my favorite funny one.
Yeah, I like it.
Yeah. Okay. So what's your winner for?
Well, the one I haven't heard today, which I saw a lot on YouTube comments, was putting a large tower or spike on the nacelle that reached up higher than the wind turbine blade.
Yeah, someone did. I see that.
Or the second spin on that is to take a cable onto a drone and then have the drone fly around, right, and provide a ground path. I think that you see that a lot. It's not a horrible idea. In fact, the nacelles do have lightning rods on them. They're not very tall. They're there to protect the equipment in the nacelle, like the anemometers and things that are on the backside of the nacelle there. But a tall rod would do a world of good. It's just mechanically, it's very hard to get a rod that's 100+ meters tall that would stay there very long. Yeah. but it's a good idea. I'd like to, just because we mentioned Ben Franklin, the kite ideas are my favorite.
Mm.
Which ones are yours, Rosemary?
Yeah, it has to be a laser. Yeah, or I think, because I'm trying to think seriously though, what technologies are improving that might change things. Because protecting the blades the way we have done is getting harder and harder, right?
Yeah.
But then some other things are getting easier and easier. Like drones are easier, predicting lightning is easier. Or will be in the future with
I hope so.
You can capture more data and process it better with AI. Perhaps we will be able to predict when lightning is going to strike some point in the future, and to do a targeted laser firing or rocket firing, just at the exact right time. So yeah, I think something like that would be my winner.
So can we call that the Austin Powers solution?
Yeah, the lasers.
Lasers on the sharks. Yeah.
Yeah.
It would work.
Yeah. Well, I guess for offshore, you could have the lasers onto sharks, or
that's what I'm saying.
Disgruntled sea bass if you can't afford sharks.
See, Joel, our co-host Joel, would love that.
Yeah. Sorry, Joel.
If he's watching, he's chuckling right now.
Yeah. I just want to finish because we're running out of time. But so the last thing I want your comment on was another thing that people say a lot to me and probably to you too. This time from Joe Blow: is there any way yet to capture electricity in a lightning strike? Because it's so much energy, and then store it in a battery or capacitor, tame it to put into electrical system. What's your thoughts about that?
There's actually not that much energy in a lightning strike. Shocking.
Why is that?
It's just the way that it is. There's just not a lot of electrons that are coming out of a lightning strike.
Because even though it's high power, it's a really short duration.
It's super short, right? It's like having I'll use an explosive analogy, like having gunpowder in a cup versus in a wrap cylinder of dynamite, right? So when you constrict things, it's very explosive. It's the impulsive nature of the energy that causes all the damage. And the lightning strikes appear very energetic, and they are from a physical standpoint, but from an electrical standpoint, they're not. We run lightning tests all the time in the laboratory that are super high lightning, simulating big lightning strikes, and it takes about the energy of a light bulb, to charge up some capacitors and create that sort of explosion. It just doesn't have a lot of energy. It doesn't have a lot of electricity in it. But it is discharged in microseconds, and when you discharge something very quickly, it becomes very powerful.
What a party pooper!
It's fun to watch. I mean, I've tested thousands of things in the lightning laboratory and blown up all kinds of things. It's pretty cool to watch, but it does feel like
not worth capturing.
No, it's not worth capturing. The one thing about being in a lightning laboratory you don't realize is that kick, because hopefully in your real life you're not next to a lightning strike, right? Because you're likely not going to live through it. But in a lightning lab where it's controlled, you can feel the explosive concussion that happens from a lightning event, and it feels like someone is kicking you in the chest.
Yeah, right.
It is really powerful. Yeah, don't play with lightning.
We tried to organize a lightning tour last time I was in your approximate neck of the woods. I hope that we still can.
We will
sometime make a video in a lightning testing facility, because that would be super cool.
Yes.
I think we better wrap up now, because we're at the hour. It went really fast and we didn't cover everything I wanted to. So maybe we'll do another one a little bit later. About some of the more, I don't know, practical experiences with lightning and how that works. But yeah, thanks so much, Alan, for your help with the video and help with the live stream. Usually I thank WeatherGuard at this point and direct viewers to sign up for your newsletter and to go check out our podcast. What did we talk about in the latest one?
We talk about all the problems that wind energy is having. Siemens Energy is going to take about a €5 billion hit on the wind energy business. TPI, which is a big blade maker here in the States, is also having some issues financially. So wind energy at the moment is in a little bit of financial trouble, but we're trying to nurse it back to health.
There's some big things going on there. So I've got links to all of that stuff in the description, so click through there. Also need to thank Engineering with Rosie Patreon team, who great supporters of the channel. I still have my bad graphic that you can't really read there, but the link is in the description. Please join us. We have a Discord server now, which is
Rosemary,
kind of
Discord.
one of the Patreons kind of forced me to create that and basically did it for me. So I, but I'm really enjoying it now because it's a really good way to have an actual discussion back and forth. And, people ask me, have I heard about, topic X? And I say, oh, I heard a really cool podcast about that and put the link in there. And somebody else will say, oh, I used to work with a guy who did that. And, it's pretty cool discussion. So that's one of the perks.
How do people join that Discord? Can anybody just join it, or do you have to be a Patreon member?
You have to be a Patreon member, and then it's actually there's something automatic with Patreon, so that it will it's pretty simple once you sign up. Yes, and the hack is that you can be any level of Patreon and you can choose an amount. So you could even just do $1 a month and you would get access to that. So if I'm inundated by 1 cent a month subscribers, then I'm like, close that loophole. But for now, that's the secret.
Can I make a plug on your behalf? Rosemary, you do really great videos. And they are spread all over the world. And people come up to me and tell me all the time, like, Rosemary's video was really awesome. And it takes a lot of time and energy to do that. So people that donate on Patreon are helping create those videos. And that's fantastic.
It does take a lot of time. Actually, one of the patrons commented on one recently, the Red Flow video. I did one on a tour of a flow battery manufacturer. And they said, I can see that that's so much work. It must be like 20, 30 hours of work. And I'm like, that video was like 60, 70 hours between me and my editor and my researcher. So that's the amount of work. And I've got a couple of helpers, Harvey and Kevin. They're both engineers, qualified engineers, and so they're not cheap, and that's why the quality is good from the work that they do.
It's very good.
Yeah. Anyway, that's a very long plug. Sorry for subjecting you all to that, but I think that's basically the end. And your plug worked because Jim's videos has said thank you and given $5 Canadian. So thanks.
All right, there we go.
Yeah, cool.
Nice. Thank you.
Okay, so this has been a good one. Thanks everyone for watching. Next video coming up will be on cement and decarbonizing it in a week or so. So
don't miss it. Yeah.
See you. Bye.